right, so I just started recording here. So these are the topics we're going to discuss today, continuing on chapter 2. The idea of the electric potential and starting point was the fact that electric field has very specific property. We looked at that and we look at the line integral of the electric field. If you remember, we did that on Tuesday, from one random point to another random point. And the way we looked at that was we did the line integral and then find a couple of interesting properties interrelated with each other. Okay, so the idea was that if we have this integral from point A to point B of E dot dl, we started looking at the electric field of a point charge, but that can be easily extended and expanded to any other charge distribution without losing generality. Okay, so the properties of this, the first thing was it was path independent. Okay, so the value of the integral does not depend on how you go from A to B. It just depends on where is the starting point and where is the end point. Okay, and that is interesting. That also means that because it only depends on the beginning and end, if you make a complete loop and come back to the exactly first point, what happens is that the integral over a closed loop of E dot dl is always 0. All right, and this combination actually means also the curl of E is 0. Okay, so these are all interrelated to each other. These are not technically separate conclusions. Okay, so if we have this situation that electric field is so specific that the curl of E is always 0, that means E, electric field, as a vector function can be always written in terms of the gradient of another function. And here convention is defining potential such that it's negative of potential. Okay, and then I'm going to say how we can calculate potential based on the charge distribution. Okay, so if we have E as a function of gradient, as a gradient of a scalar function, this always satisfies the condition that the curl of E is 0, because the second derivatives that we discussed, the curl of the gradient of any function is always 0. Okay, so far so good? So I'm basically recapping what we discussed previously. Okay, so we have this one, and then we define the integral form of the electric potential based on this. The V at any point R defined as the integral, negative of the integral of E dot dl, starting from a chosen origin to the point that we are. So the position is the end limit of the integral. The beginning of the limit is an origin. We are free to choose whatever origin we want. A lot of time, I would say most of the time, this origin is at infinity. Okay, because if we are away from trivial charge distributions, the electric field vanishes, and we can assume that the electric potential at those points are 0. Okay, there are very special cases we cannot make that assumption, and those special cases are the cases where the charge distribution actually extends to infinity as well. An example of that we did was infinite plane with uniform charge distribution. Because the plane goes all the way to infinity, you cannot assume that electric potential at infinity is 0. Okay, but that's sort of an exception. Usually the origin, 0 potential at infinity works well with most trivial charge distribution. Okay, so if we have this definition, we show that this is equivalent. This is few lines of mathematics. I'm going to skip that because we did that on Tuesday. And this is exactly equivalent of saying that electric field is negative of the gradient of V. Okay, so if you have electric field, you can calculate potential like this. Or if you have potential, you can have electric field like this. So here I want to remind you the basic idea of using electric potential is finding an easier way to calculate electric field. Okay, so except a few starting examples and definitions, we don't usually work with this. Most of the time, the E, electric field, is a question. Most of the time we have the charge distribution and we try to find the electric field. And that means we should move from the charge distribution to electric field. And sometimes, I would say most of the times, it's difficult to do that directly. So what we do is that we calculate potential, which you will see is easier to calculate. And from the potential, we calculate electric field. Okay, so this is how electric potential is a useful quantity as a whole. Okay, otherwise, potential on its own does not have much physical meaning. Electric field does have, because that's directly related to the field, and that will be related to force and, it's related to force, and that can be related to the work and energy, etc. Potential on its own is a mathematical definition. It's not a physical quantity that you can easily measure. Sounds good so far? Okay, so with this definition and starting point, I'm going to discuss a few points about potential. Number one, I'm following the same order of the textbook, the name of the potential. Okay. The name can be actually confusing. Can anyone guess why it can be very confusing? I'm sure you are very familiar with potential energy, right? And in physics, if you hear potential, that's potential energy a lot of times, right? Electric potential is not potential energy. Electric potential can be proportional to potential energy, but it's not potential energy. Even if you look at the units of the electric potential, it has a different units, okay? Can you help me figuring out what is the unit of the electric potential? We should be basically being able to do that through this equation or this equation, either of them, it doesn't matter. So let's look at this. The unit of the V, electric potential, of course, eventually it has a name of volts, but let's look at that in comparison with energy and potential energy. The unit of this is unit of electric field. What is the unit of electric field? Come on. Electric field is force divided by electric charge, right? Is that correct? Right, so this was, I would say, the basic definition of electric field, right? Force is Q times E. Unit of force is Newton. Unit of electric charge is Coulomb. So E should be Newton over Coulomb. So Newton over Coulomb. And then we have dl here, which is meter. These are all SI units. Newton meter over Coulomb. Newton meter is energy, right? So that is Joule over Coulomb. Okay. So the unit of electric potential is not energy, it's energy divided by electric charge. Okay, and the name of this is volt. Okay, so V is not energy, but if you multiply Q by V, then the unit of this is energy. Sounds good? Okay, so the next thing is something that I emphasized always as I define the potential is what is the advantage of using potential? Okay, this is I already talked about, and we will see that over and over again whenever we are working with potential. So the basic mathematical advantage, as you can see, potential is a scalar function. From that, we can easily, not easily, but directly, we can calculate electric field. How many parameters electric field has? It's a vector field. In 3 dimension, E has 3, right? It has 3 parameters. Okay, so that means almost like 3 scalar functions combined together. Electric potential is a scalar function, 1 parameter. Okay, so at the first level, it looks like electric field has 3 times more information than electric potential, because electric field is a vector function with 3 components. Okay, so now what's happening here is that electric field, yes, it has 3 components. You can always say it has Ex, Ey, and Ez. Each of them is a function of 3 parameters, x, y, z. So these are 3-dimensional functions. But the point is that these 3 components are not completely independent of each other. Okay. If you look at the equation of curl of E equal to 0, that means very specifically certain components of electric fields are related to the other components. Okay, and that means if you want to make the curl is 0, for example, what we should have is this. We should always have partial derivative of Ex with respect to y should be equal to partial derivative of Ey with respect to x. Okay, so we need to satisfy these conditions in order to make the curl of the electric field become 0. So what does it mean? That means all these 3 components are not completely independent of each other. They are dependent. Okay, certain vector functions can never be an electric field because of the curl not being 0 and because these conditions are not satisfied. Okay, so what electric potential does is that it takes this information and summarizes them in 1-dimensional scalar function. Okay, I mean 1-dimensional not in the sense that it's function of 1 variable, in the sense that it's just a scalar function with 1 parameter instead of 1 component. Sounds good? Okay, so number 3 is the origin. And that's pretty much already discussed when I said here you can choose an origin. You are free to choose origin at any point. A lot of times we said we use infinity as origin. What happens if you choose a separating point, a different point at origin? Well, let's imagine I have a point charge in my hand and I'm going to try to calculate electric potential around this point charge all the way to infinity. Okay. Everybody says potential at infinity being 0 is a very good choice. And suddenly I say, no, I don't want to do that. What I want to do is that I want to set the potential 2 meters away from this electric charge, be 0. And at any point closer to the electric charge, if it's positive, it's going to be a positive number. Beyond 2 meters, if it's a positive charge, it's going to be a negative number. Can I do that? Yes, I can. What I am doing is that I am just changing the value, okay, of the electric potential that I'm calculating and measuring. The value of the potential is not much important. What is important is if I go from this point to this point, how much the electric potential changes. Okay, so that's important point. Other than that, if you have a function for electric potential in a space, you can easily add a constant or subtract a constant, and that still is the potential defining the electric field and everything on. Okay, so origin we are free, and if we change origin, we are just changing the electric potential by a constant value, and that's not really important. Okay, because what's important is the difference and change of electric field. Or in differential terms, the gradient of the electric potential. If I change electric potential and add a constant to it, the gradient of that constant is 0, and that completely vanishes if you take the gradient of that potential. Sounds good? Okay. So number 4 is the superposition principle. Okay. So at the beginning we said superposition principle, meaning that if we have multiple charges and multiple fields acting at one point, we said based on mechanics, if we are calculating forces, we can just add the force vectors together, and that's going to, the net force is going to be the actual force acting on a particle. Okay. And from the relationship between the force and electric field, we could say that the same principle is correct for electric field. Imagine there's one point in a space and I have multiple different charge distributions and I want to calculate the net electric field right at this point. It's enough for me to calculate electric field from each of the charge distribution, and it's going to be multiple electric field vectors. And if I add them, I can calculate the net electric field. Okay, that's technically the superposition principle. And moving from force to electric field all the way to electric potential, for potential, we can do exactly the same thing. If we have multiple charge distribution creating multiple electric potential, let's say at one point in the space, if we have V1 at point R, and if we have V2 at point R created by two separate charge distributions, what we can do is that we can just add them, and that's going to be the net electric potential at any point. Okay, so superposition principle works all the way from the force to electric field and to electric potential. Okay. Point number 5 is the units of potential, and that is what we already worked out in number 1. Okay. Any question? So these things are more or less clear for you guys? Hopefully.
Yeah.
I have a question regarding the fourth point about superposition. So it means that for any electric field of n charged particles, you can find the force by simply adding them?
Yes, you can find electric potential by algebraically adding them. Okay, imagine you have n point charges and you want to calculate electric potential at one point. Okay, so all these point charges contribute and you can calculate electric potential from each of those point charges and just add them up algebraically if it's electric potential. If it's electric field or force, you can still add them up, but you got to be careful that you're adding vectors. So you should follow the protocol for addition of vectors.
All right.
Sounds good?
Yeah, thank you.
Okay. So now how about doing one example? So I completed this and this so far. So this example is from the textbook. I don't know which one, but I can say the question is pretty straightforward. The question is, we have a sphere, or more precisely, a spherical shell that carries electric charge of Q on the surface, okay? The sphere has a radius of r, and the question is, what is the electric potential all the way outside the field, outside the sphere, and also inside the sphere? Okay, so this is a shell and not a solid surface, not a solid sphere, and we are trying to calculate electric potential. dr in the space. Okay, so it's one of those cases we have a spherical symmetry, so we don't need to be worried about the angles of theta and phi. Everything has spherical symmetry. What we are basically need to find is potential at point R, where we are away from the center of the sphere at distance R. Okay, so to calculate electric potential here, this is a case that we already know what the electric field is. Okay, so we can go to the integral definition of the electric potential, which says V of R is equal to the negative of the integral from certain origin to R of E dot dl, and this R should be a vector. Because of the spherical symmetry here, we can drop the vector sign because we are calculating as a function of distance to the center of the sphere. Okay, so for this specific case, it's okay to use R as a scalar, and that's technically the radial components of the position in spherical coordinates. Okay, so now we know what E is, right? E outside such a sphere, we calculated, I think last week, it really behaves like point charge. So E is 1 over 4 pi epsilon 0 Q, which is the total charge on this shell, divided by R square times R hat. Okay, so it's a unit vector in radial direction, and this is E as a function of R. Okay. But this is the electric field outside, right? What is the electric field inside the sphere? This is a shell with no charge distribution inside the sphere. What is the electric field? This is something you should be able to answer very quick.
On the inside?
Your Gauss law, if you calculate the electric field, you integrate that, that should be equal to charge within the sphere. And since we don't have any charge within this sphere, electric field inside the sphere is going to be just 0, right? So inside, no electric field. Okay. So now, if we are outside, R is always greater than radius of the sphere, we can calculate this electric field. E dot dl, you can imagine that dl for a spherical coordinate is dr times r hat plus r d theta, theta hat plus r sine theta d phi, phi hat. And if we do the dot product, you can imagine that the second and the third component here are irrelevant because the first component is only in r hat direction. So E dot dl is simply 1 over 4 pi epsilon 0 Q over R square times dr. Okay, and that is basically the dot product of E times the first component dr r hat. Okay, the other components theta hat and phi hat are perpendicular to the r hat, so they don't give any meaningful. They just 0 after the dot product. Okay, so E dot dl is a scalar. The first term is a constant. Q is a constant. So basically, we only have dr over r squared. I'm going to continue the integral here. Vr is negative integral. I'm going to choose infinity as a reference point. So I'm integrating from infinity to r. You know what? Let me take the constants out of the integral first. 1 over 4 pi epsilon 0 Q over 4 pi epsilon 0 integral from r equals to infinity to r, and here I have dr over r square. Okay, so the integral of dr over r square is 1 over r, negative of 1 over r, that cancels out with this negative sign here, So that becomes technically 1 over 4 pi epsilon 0 times Q over R from infinity all the way to R, and that is 1 over 4 pi epsilon 0 Q over R. Okay, and a better way of writing this, not to confuse this R with the R inside the integral, is that using prime coordinate for things that are inside the integral. So something like this. So that this R only refers to the limit of the integral and not the radius inside, because this is the integral parameter. Sounds good? So this is the potential. This is equation for the potential from outside the sphere all the way to infinity. Okay, so I'm gonna now write here that VR is 1 over 4 pi epsilon 0 Q over R. Sounds good? How about inside? What do you guess about the electric potential inside the sphere? Let's start by asking, is it a constant?
Yes.
Is it 0?
Yes.
0
Yes.
or constant?
0.
Okay.
Why isn't 0
So
constant?
let's start by this. Why is it a constant? Why can you quickly say it should be a constant before even doing this integral? I'm going to tell you how you can answer this question very quick. Okay. If you look at the differential definition of the electric field as a function of potential, we had the gradient of V. Okay, electric field was equal to negative of the gradient of potential. Okay, now we already know that the electric field inside the sphere is 0. Is that correct? Electric field being 0, electric field is derivative of the potential. Okay, so if this is 0, potential should be constant. Okay. So wherever there's no electric field, that means potential is constant. As soon as you have certain electric fields, that means potential is changing based on how the behavior of the electric. Okay, so you should very quickly say electric potential is constant because there's no electric field. So now the question, is it 0 or not? That's a big question, okay? Because we already assumed that origin is at infinity. Okay, so if you go to infinity all the way, the potential is 0. That you know. And as you get closer and closer to the sphere, what happens is that electric potential increases. I'm assuming that the charge Q is a positive charge. Okay, so if I want to draw VR as a function of R, if this is the radius of the sphere, I would say at all the way at infinity, potential is 0. And as we get closer to the sphere, it increases. Okay. The way it increases is defined by this function. So it's inverse of R, so it increases exactly with the same behavior as 1 over x function. Okay. Or I better say 1 over R because that's what we have on x-axis. Okay, so this is how electric potential increases. Now we get right here to the surface of the sphere. We get to the surface of the sphere. One thing about the electric potential that we will discuss, there's never a discontinuity in electric potential. Okay, potential is always continuous. Okay, the slope can be discontinuous, that's fine. But the value of the potential is continuous. Okay, and I'm going to tell you why in a minute. So you cannot have electric potential having this value here and continuing 0 inside the sphere. Whatever the electric potential is here, okay, that has to be the same and constant inside the sphere. Okay, and this is just based on the interpretation of that. We said the electric potential needs to be constant, So as soon as I find the value of the electric potential on the surface of the sphere, I should be able to guess what it has to be inside, because it needs to be continuous on the surface, whether it's zero or not, whether it's constant or not. In this case, it's constant, okay? So now, why do I insist that there should not be any discontinuity in electric potential? That comes exactly from this definition again. Electric field, which is a physical quantity, which is correlated, which is proportional to force, is a derivative of the electric potential, okay? Now imagine if you have discontinuity in electric potential right at the surface, what happens? That means you have one point, which is right on the surface of the sphere. Electric potential changes so much, okay, because it's discontinuity over very, very tiny displacements, okay? And that means electric field becomes infinitely large. That's not going to ever happen. You're not going to ever have infinitely large force, okay? Because electric field is derivative of this, you can never find any discontinuity in electric potential, okay? And of course, this is going to be even more obvious if you follow the integral definition of the electric potential, okay? So what's happening if you run this integral instead of point R, which is outside, you run it all the way to point R, which is inside the sphere. What you are doing is technically doing this integral all the way from infinity to not R here, but to capital R, which is the radius of the sphere, and then continuing it inside, okay? So electric field, electric potential is calculated based on this integral. It adds up to the surface, and if you continue, there should not be any discontinuity, okay? You will have just one more contribution from a second integral, okay? So if I want to write that mathematically, very similar thing for points that R sits within the sphere, I should write it like this. VR is this integral minus Q over 4 pi epsilon 0 integral of R prime from infinity to the radius of the sphere, dr prime over R prime squared, plus another integral, or I would say minus another integral because we have negative sign here, Q over, oh sorry, this is not this, the integral of, I would say, E dot dl, okay, for position of R prime equal to R, all the way to R, which is inside the integral, okay? And here we have E of R prime, which is a point inside the sphere times dl. Okay, now look at this. The whole thing here, this integral, should be potential on the surface. That means this definition divided by capital R. Okay, so it is 1 over 4 pi epsilon 0 times Q over R. Okay, so this is the whole integral here. And the second integral here, because of the electric field being 0, inside the sphere, the whole thing here becomes just 0. Okay, so you end up having electric potential being a constant minus 0, and that constant is electric potential right on the surface of the sphere. Sounds good? Can you guys see the last line? I don't think so. Okay,
I can't really see it.
yeah. Okay, so let me continue next on this side, okay, which makes it 1 over 4 pi epsilon 0 Q over R minus 0. So this is the first integral, which is constant, independent of the radius, and the second term is just 0. The capital R is a constant, and that's the radius of the sphere, not the radial component of the distance.
What does that last integral show us with the two-part one?
This one?
Yeah, yeah, like the whole thing.
Okay, so this one is like if you are inside, you're running your integral from all the way to infinity. Okay, so coming all the way from infinity to this point, let's say.
Okay.
The first integral is this part, which runs all the way to infinity. The second integral is this part.
Gotcha. Thank you.
Sounds good? Any more question?
I have a question.
Sure.
So mathematically, the potential cannot have discontinuity in its derivative, right?
The potential can have discontinuity in the derivative. Okay, like here, the derivative is 0, and here you have some certain derivative. But it cannot have discontinuity in its value. So here we have discontinuity in the slope. We have discontinuity in derivative, but not discontinuity in potential.
Okay, so everything is good as long as each point is defined.
Yes, exactly. Each point should be defined. Okay. So this example, I'm gonna come back to this, repeat this with a different approach. Later on, hopefully during this lecture, we have time, this 10, yeah. Hopefully we have time for this. Okay. Any more question on this? You guys are good? Okay, so I'm gonna erase this and move on to the next topic. So, done with this example too. All right. So here what I want to do is that I want to focus on the differential format and definition of the electric potential. Connect that to electric field. And then I want to again focus on the differential format of the Gauss law, which connects electric field to any charge distribution. Okay. So, and from that we're gonna find Poisson's and Laplace's equation. Okay, so. Okay, so differential relationship between electric field and potential is that electric field is negative of the gradient of potential. Okay, and then for the electric field we had, from the Gauss law we had the divergence of the electric field is 1 over epsilon 0 times rho, rho being the volume charge density. Okay, and we also had the relationship that the curl of E is 0. With this definition, the second equation is always taken care of. If you define electric field as a function of the gradient of a function, as I said a couple of times already, the curl is always 0. So we don't need to worry about this. But now let's look at this one. Divergence of E is proportional to charge distribution. And if I substitute and write electric field in terms of this negative of the gradient, what I have is negative of the divergence of the gradient of V is 1 over epsilon over rho. Divergence of the gradients, I don't know if you remember or not, I said it's very famous because divergence of the gradient happens a lot in physics and people call that Laplacian. Okay, So mathematically, divergence of the gradient, of V is written as del 2V. And if we write it in terms of the components, this is equal to second derivative of V respect to x squared. I'm using Cartesian coordinates. Second derivative of V with respect to y plus second derivative of V with respect to z. Sounds good? So this is Laplacian. And here what we have is, if we have any charge distribution, Laplacian of V is equal to the negative of 1 over epsilon 0 times charge density. And this is the so-called Poisson's equation. Okay, so second derivative of electric potential with respect to space is proportional to the charge density. Okay, so what happens a lot of times, if you are solving an electromagnetic equation numerically, and if you have charge density, this actually sets up a differential equation for you. The charge density, you can imagine this is given, and then you are trying to find the electric potential. Okay, so this is when you have charge distribution. What happens more often than not is you have charge distribution, but you are not interested in calculating the charge distribution, the electric field or potential inside the charge distribution, but at certain points that you are away from the charge distribution. And that happens very often. And if you are away from any charge distribution, the Laplacian of V is always 0. Okay, this does not mean that we don't have any potential, but this says that at any point away from charge distribution, the second derivative of V is 0. Okay, that doesn't mean V is constant. V can have all sorts of different shape and behaviors, but the second derivative of this is constant. This equation, Laplace's equation, and this one, which is, Poisson's equation, and this one, which is Laplace's equations, are differential equations. Okay, so you know, if you want to solve a differential equation, part of that is the equation should satisfy, the function should satisfy the equation. Equally important part is that the equation should satisfy boundary conditions. Okay, so a lot of times all these electrostatic problems is not about, the difficulty is not on satisfying the equation, the difficulty is satisfying the boundary condition. Boundary conditions are where we have the charge distributions. Okay, it could be a surface charge or anything like that. Okay, so these equations alone are necessary, but we also need boundary conditions in order to calculate electric potential from this. Okay, so this is something that we will work a lot in chapter 3, that we want to calculate electric potential based on certain charge distribution, and we use a lot of mathematical tricks to make that happen. Okay. And one characteristic of Laplace's equation is that the difficulty is so much dependent on how many dimensions you have and what dimension you are working on. Okay. If you look at the one-dimensional Laplace's equation, that's simply a second derivative, is very easy thing to solve. Okay. That's just kind of a straight line kind of thing. If you move on to 2 dimensions, that's going to be a little more difficult. If you work in 3 dimensions, that's a lot more difficult. We will be discussing certain mathematical tools and tricks to calculate Laplace's equation. Okay, but what I can tell you is that these 2 equations alone, okay, are fundamental methods of calculating potential, which eventually gives you electric field from charge distributions in this differential form and format. Okay, so
I have a question.
with this definition, I'm going to stop talking about the Poisson's and Laplace's equation, and we come back to this in chapter 3. Yes, there was a question?
Yes. So what's the main difference? When do you set it up equal to 0 and equal or equal to phi over E0?
If you are away from charge distribution, you got to use this one. Okay, so if I want to symbolically show it to you. Imagine you are in a space, you have certain charge distribution in a space, rho, okay? And then you are interested in calculating potential and electric field in the whole space here. Okay, so here there's no charge distribution, so the Laplacian of V is 0. Okay, here we have charge distribution, so the Laplacian of V is negative of 1 over epsilon 0 times rho.
Okay, thank you.
Okay, and this happens more often because usually the space around this is usually bigger. Okay, and of course it depends on application as well, but this is very common. The Laplace is equal.
So when the Laplacian is equal to 0, it just means that there's no charge, meaning that it's just that there's no charge.
When there is no charge distribution, the Laplacian is 0. Yes.
So but you said like if it's too far away, but how, until what point you start counting? Like until you get to the edge of this charge
It
distribution?
depends. It totally depends on your application. Okay. So usually it depends. I mean, what accuracy you want, but I've done a lot of numerical calculation on electric potential, and it's always possible to estimate how far you want to go and where you really want to set it to 0. Okay, if you're doing numerically, you never have an actual infinite, so you make this box big and big to the point that you are certain it's big enough, and you set electric potential being 0 at the boundary of the box. Something like this. If you are here, you say V is 0 on this. Okay, so how big is it good? There are different ways. If you are doing numerical calculation, what you can do is that you can move your box and make it a little bigger from what you had.
Got it.
Make
Yeah.
it a little bigger, and then you can see if that is making any effect or not. Right? If you make it a bit bigger, it does not change anything. That means it's already big enough. That's
Okay.
all.
Thank you.
Professor, just to be clear, the first equation is the Poisson's, right? And the second one
This
is
is
the
the Poisson's equation, and this is Laplace's equation.
Okay, thank you.
Cool. Okay. Any question on this? All right, so if you're good, I'm going to move on, and I'm going to look at the potential of a localized charge distribution. Okay, so what I want to do is this. I want to now focus on point charge and say, if I have a point charge here, what is the proper way of formulating and calculating electric potential around this one single point charge? Okay, and then I want to do a usual trick and say any possible charge distribution is combination of point charges. Okay. And if it's combination of point charges, and if the superposition principle is valid, what I want to do is that I want to define an integral that can tell me electric potential at any point in a space based on the charge distribution around that point. Okay, and that's sometimes useful. I want to do that, and hopefully I have time to go back and do the example of the spherical shell with the new definition of electric potential, which is integration of contribution of many, many point charges that defines potential at any point in a space. Okay, so the discussion here, conceptually, I say it's trivial, and some of the mathematics are also similar to the mathematics I already did for the previous example. So I hope we can move on fast in that one. So let me get rid of this. Okay, by the way, localized charge distribution, I mean the charge distributions that do not extend to infinity. Okay, if it extends to infinity, that messes up with certain things. The most important thing is you can no longer assume electric potential is zero at infinity. Okay, so localized means it's just random, any possible shape, any possible size, but not extending to infinity. Okay, so let's start from point charge. Imagine I have a point charge Q at this point, and I know the electric field around the point charge is 1 over 4 pi epsilon 0 Q over R squared times R hat. And based on the previous example that we did, I can define electric potential of a point charge as 1 over 4 pi epsilon 0 Q over R. Okay, so potential is a scalar function. We don't need to use the R hat, the unit vector anymore. And you will see that makes certain integration a lot easier. Okay, doing an integral over to calculate E from random charge distribution can be very difficult because you're going to add all these vector components. For potential, it's a scalar, and you will see we can make things a lot easier. Okay, so this is the charge, the potential from a point charge. From one point charge. All right, so now imagine instead of one point charge, I have many point charges. I am going to call them Q1, Q2, Q3, and so on. Okay, what I need to do to calculate potential at position R, this time I rather use the vector on the top of this. Okay, at position R, what I should do, I should add up contribution from all these different point charges. Okay, and I'm going to use a sigma. I want to say that V at any point R is 1 over 4 pi epsilon 0. That's a constant. But then I have a summation over different point charges. I would say it's Qi, where I runs from 1 to n, assuming that n is the total number of point charges I have. It's Qi over, here I want to use Ri, script R, which is the symbol of distance vector. Okay, that means if the point R is here, if this is R, the Ri is the distance from each of the point charges to the point that I have. Okay, so this is, for instance, this is R1, this is R3. These are distance vectors. Okay, so with this summation, I can calculate potential at any point based on the position of the charges and value of the charges. Okay, so far so good? And now imagine instead of many point charges, I have a continuous distribution of charges, continuous charge distribution. That means I have a volume charge density. What I need to do is that I need to modify this so that it includes continuous charge distribution, meaning that this sigma should change to an integral. Okay, so this is potential from many point charges. Okay, and so here we got VR. I'm going to change it to an integral 4 pi epsilon 0, the integral of dq over distance vector. Okay, so this is for continuous. Charge distribution. Looks good? Is it clear how we started from a point charge to multiple point charges and now continuous charge distribution? We did that before for electric field. We do this and we will have similar type of approach for magnetic field as well, starting from one point and then combining everything and then continuous distributions. Okay. And do you remember how we define dq? That depends on the geometry we have, right? If we have volume charge distribution, dq is volume charge density times d tau. This is an element of the volume, and dq is a charge, rho is the volume charge density. If we have surface charge distribution, dq can be written in terms of the surface charge density times the element of the surface. If we have line charge distribution, dq is lambda times dl. This is infinitesimal displacement of length. Sounds good? So dq really depends on what sort of charge distribution we have. And then we should decide which one to choose. In a very general format, we will have all these three types of contribution adding up. So three integrals. If we are in a system that we have volume charge distribution, we have surface charge distribution, and we have line charge distribution as well. We just add them. Sounds good? All right, so I'm gonna do one example to calculate electric field based on this integral, electric potential based on this integral, and the example is exactly the same example we did before. We are just using a different approach, okay? The question, the system is a spherical shell, and now instead of integrating electric field, I'm just integrating the potential created by each small pieces on the surface of the shell. All right, so let me erase this and I'm gonna redraw the system. Any question on this? Everybody is good? Everybody happy?
I have a question. So
Sure.
dq is just the dimensions of the problem?
dq is the infinitesimal charge. Okay, so depending on the charge distribution and dimension of the problem, dq mathematically will be calculated differently if we have continuous volume charge distribution or we have surface charge distribution or line charge distribution. Okay, so in the example I'm going to do, because we have surface charge density and charges distributed on a shell, we're going to use this one. That's one example. Sounds good?
Yeah, thank you.
Okay. Okay, so the example is example 2.8 from the textbook. Okay, so what we have, very similar to previous problem, there's a spherical shell. Okay, with the surface charge distribution of sigma, meaning that we have this sphere, all the charge Q is distributed uniformly on the surface of the sphere. And the question is, what is the electric potential at distance r from the center of the sphere? We're gonna do the same assumption that the electric potential is 0 at infinity. Okay, so now, what I want to do is here, I want to integrate the potential from each small pieces of this surface. Okay, so we said that VR is 1 over 4 pi epsilon 0 integral of dq over r. Okay, here we have surface charge distribution, so I would write it in terms of the surface charge density, 1 over 4 pi epsilon 0 sigma dA prime over r. Okay, and this dA prime is the surface element, infinitesimal area on the surface of this sphere. Okay, so to continue, let me choose where is the center of this sphere, and also let's draw the Cartesian coordinate axis. This is X, this is Y, this is Z. Okay. Because of the symmetry of the problem, without loss of generality, I can choose to calculate electric potential at one point on the Z-axis. Okay. It doesn't matter we choose this point or something on the Z-axis because everything is symmetric. So whatever we find as a function of Z, the same thing will be true as a function of radius. Okay. So let's imagine this is Z. Okay. Now, what we are integrating on dA prime is one point like this. Okay, so this dA prime is a very small patch on the surface of the sphere. Okay, so this is dA prime. And the function R we have here is actually defined by the distance of this point to the position that we are calculating electric field. So it's going to be like this. This is the distance vector. Okay. And the radius of this sphere is R. So this distance to center is R, capital R. And the angle here is theta, the radial component. And because we are using this within this integral, I rather use theta prime. So this is part of the prime coordinates that we have. Okay. So basically the integral runs over the whole surface of the sphere. Okay. And we add up contribution of each of these small pieces to the potential created at this point. That's what we are conceptually doing. Okay. So to do that, we need to formulate what is that this distance in terms of the Z, in terms of the radius of the sphere, and in terms of theta. The distance is a function of theta, Z, and R. Okay. So for that, we use a cosine rule, R squared. By the way, we only need the magnitude of this. The direction doesn't matter because for potential, we only need the magnitude. The direction does not matter. We add things algebraically. We have R squared being R squared plus Z squared minus 2RZ cos theta. Okay, so this is magnitude of R in terms of radius of the sphere, position Z, which is where we are measuring potential, minus 2RZ cosine theta. This is basically the cosine rule for this triangle that I have on this. Sounds good? And then the surface of element, dA prime, this is the area on the surface of the sphere. If you remember for a spherical coordinate, I said there are three ways that you want to look at this, the infinitesimal area. And this is, if this is on the surface of the sphere, we are talking about something with the radius being constant and equal to capital R. So R squared sine theta prime, d theta prime, d phi prime. It's a surface element, okay. And the limit of integrals, R is constant, theta is changing from 0 to pi, and phi is changing from the 0 to 2 pi. Okay, that's what we have this integral over. Okay, so I'm going to continue here. I'm going to write dA prime as a function of this and R squared as a function of the whole thing I have here. So I'm going to use these two and swap them back into the integral. It's going to look a little long, but it's totally manageable. Okay. So
Professor?
Yes.
For the R squared equation, what is in front of the capital R, the minus?
Minus 2RZ.
Gotcha. Thank you.
Okay. So VZ So instead of writing VR, I'm going to write VZ because everything is at the end a function of Z, and that is technically the distance from the center of the sphere that I have, okay, is 1 over 4 pi epsilon 0 times, the sigma here is a constant, so I take it out of the integral. I write it sigma over 4 pi epsilon 0, the integral of dA, here is r square sine theta prime, d theta prime, d phi prime over r square is this. We have r here, so we need to take the square root of this, which makes it r square plus z square minus 2rz cos theta. Okay, so here again, the integral is over d theta prime and d phi prime. For each of them, d theta prime runs from 0 to pi, d phi prime runs from 0 to 2 pi. Okay, so basically it's a double integral with phi prime running from 0 to 2 pi and theta prime running from 0 to pi. And now if you look at the integrand, there is no phi dependent. Okay, so that means we can easily get rid of the integral here for pi, for phi, okay? So I can just quickly do the first integral. I'm just gonna get rid of this. Okay, and that's gonna give me a 2 pi factor. Pi sigma, and I'm gonna say that this is the integral of d phi prime from 0 to 2 pi. Okay, and then I get rid of this. So I did one of the integrals, okay? And here I have r squared sine theta prime d theta, and here I have cosine theta prime. By the way, this is theta prime, okay? And this can be easily done with the change of variables. So if the whole thing here, cos theta prime is x, sine theta prime d theta prime is proportional to dx, okay? So with this combined, I can write the integral in terms of by the way, r squared here is a constant as well. So I can take this one out of integral 2. Sounds good? So I have this, and then all these constants, and 2 pi cancels out with 4 pi. So outside the integral, things become a lot more simple. We get sigma r squared over 2 epsilon 0. And here we got the integral of sine theta prime d theta prime over the square root of r2 plus c2 minus 2r c cos theta prime. Okay, so this is the VZ. Okay, and this integral becomes equal to sigma r squared to epsilon times 1 over rz square root of r2 plus c2 plus 2rz cos theta prime. And here limit of theta is from 0 to pi. Okay. So cos theta prime, if theta prime is 0, cosine of 0 is 1. If theta prime is pi, cosine of that is -1. Okay, so technically this parenthesis is going to give me 2 terms. Okay, and if I write that, that's going to be, can I continue here? Or you know what, I'm going to continue on the top because I'm not sure if I have a space here. Okay, so continuing all the way up here, I can write it in terms of Vz equal to sigma r squared to epsilon 0, parentheses. The first term at pi gives me okay, I have r and z here. I can take that out. That means I can get rid of this and add one z here. A square root of r2 z2 plus 2rz. Yeah, I think this should be a negative sign. Minus square root of r2 z2 plus 2rz. And this is negative here. Okay. So the limits, each of them give me one term. And if you look at these, this is basically r plus z square. And this one is r minus z square. Looks good? I'm almost out of time. I'm going to do one more step, okay, and then we're going to leave the discussion on the result of this to next Tuesday. Okay, so I'm going to get rid of this now. Continue here that Vz is sigma r over 2 epsilon z. And here we have r plus z to the power of 2 under the square root. That means that's like absolute value of r plus z. And the second term is r minus z square under the square root. So that is the absolute value of r minus z. Okay. So we did this integral, started here and came to this point without the assumption of z is either inside or outside. So this is pretty general, whether we are inside or outside the sphere. The interesting thing is that the sign of this absolute value will change, whether z is smaller than r or bigger than r, okay? And based on that, if we are inside or outside, we're gonna get different values for the potential and different kind of dependence on the distance. And what we expect is that outside the sphere, we're going to get a decaying potential, and inside that, it will be constant. Okay, so everything is kind of hidden inside the sign of r minus z. Okay, so the time's up. What I want to do is that I'm going to stop here, and on Tuesday, we start from this point, and we'll discuss the next for this potential. Okay, so anyone has question on this so far?
Nope, just
No? Okay.
a lot of
So,
integration.
so any other question before we finish the session? No? Okay, everybody's happy? Okay, so I'm gonna stop
Happy as
here.
a clam.
Okay, I'm gonna stop the lecture. Was there a question?
No, I said I'm happy as a clam.
Okay. Okay, so I'm gonna stop here and then see you guys on Tuesday morning. We're gonna continue this on Tuesday.